Hi, my name is Lakshya Jain and this is my video for solution of maths and examination question number 4. So let's get started. So the question given to us is that we need to solve the given non-homogeneous linear ordinary differential equation, that is y double derivative plus 9y is equal to cosec x. So I'm going to use the method of variation of parameter in order to solve it. So now we know that any solution of second order homogeneous linear ODE is of the form is the addition or the superposition of two solutions yh and yp, where yh is basically the general solution of the corresponding homogeneous equation of the given non-homogeneous linear ODE, and yp is the particular solution for that is a particular solution, and in the case of method of variation of parameter, it was given by Lagrange. The formula for calculating yp was given by Lagrange, right? So for the first part, I'm going to calculate the yh, that is the general solution of the corresponding homogeneous equation, that which in this case is y double derivative plus 9y is equal to 0. Right now, comparing it with the general second order linear ODE homogeneous of the form y double derivative plus a y derivative plus b y is equal to 0, we get that a is 0 and b is 9, right? So in order to find the solution of yh, we have to solve an auxiliary or a characteristic equation, as it is called, of the form a lambda square plus a lambda plus b is equal to 0. Let's substitute the value. We get lambda square plus 0 plus 9 equals 0. This implies lambda square plus 9 is equal to 0. On solving, this yields lambda is plus minus 3 iota. Now, when the solution of this characteristic equation are a complex number, the solutions of yh are of the form minus ax by 2 plus I omega and minus ax by 2 minus I omega. Omega, which is, let's calculate it, is given by the formula half under root 4b minus a square. So let's substitute the values. This gives us 4 into 9 minus 0. So half into 6, and this gives us 3. Right. So now, using Euler's formula and then adding, subtracting and multiplying by suitable constants, we basically get that y1 is of the form minus ax by 2 cos omega t, and y2 is given by e raised power minus ax by 2, oh sorry, this is x here, x by 2 sine omega x, right? So let's substitute the value of omega in a, and this yields us e raised power 0 cos 3x, and this yields us right, so basically this right, so yeah, right, basically this yields us e raised power 0 cos 3x, and this gives us e raised power 0 sine 3x, which is sine 3x, and which is cos 3x, right? So now this yh is the superposition of these these two solutions, y1 and h2. So a cos 3x plus b sine 3x is our yh, where a and b are constants that belong to real numbers, right? So a and b are constants that belong to real numbers. Right. Now, for the case of yp, that is the particular solution as given by Lagrange. This is given by the formula C1 y1 plus C2 y2, where y1 and y2 we had just calculated. That were the solutions of the homogeneous yh. The solution of the y1 and y2 are basically cos 3t and sin 3t that were just calculated, right? So, and C1 and C2, the coefficients that we have written here, are given by minus y2 r divided by W, and C2 is given by y1 R by W. Let's know what these R and W are is. So W is basically the Wronskian, that is given by y1 y2 y derivative 1 y derivative 2. So W is defined in this way. Let's find the value for W in this case. Y1 was cos 3t, y2 was sin 3t. The derivative of cos 3t is minus 3 sin 3t, and the derivative of sin 3t is 3 cos 3t. Right, so let's find the value with 3 as common. This gives us cos squared 3t plus sin squared 3t, and this yields is 3. So the value of W in this case is 3. Now R is basically the RHS in the non-homogeneous linear ODE when it is in general form. So in this case R is given to us as cosec of x. So now since we have W and R and y1 y2 with us, let's get to finding C1 and C2, and before that I forgot to place the differentials dx here. Right, so let's find the C1 coefficient C1, that is given by minus y1 R by W dx. So let's substitute the values. Y1 we have sorry, this is y2 here. Y2 is sine 3x, R is cosec of x, and W is 3 dx. Right, so this gives us minus 1 by 3 integral sine 3x by sine x dx. Now I'm going to use the identity that sine 3x is 3 sine x minus 4 sine cube of x. Right, I'm going to substitute this identity, and giving us 3 sine x minus 4 sine cube of x divided by sine x dx, giving us minus 1 by 3 integration 3 dx plus 4 by 3 integration sine square dx on splitting the terms. Right, this integral yields us minus of x, and in this integral I'm going to use an identity that 2 sine square x can be written as 1 minus cos 2x dx. So the identity used is that 1 minus cos 2x is 2 sine square x. So let's integrate this term here. So C1 yields us minus x plus 2 by 3 x and minus 2 by 3 into the integral of cos 2x is 1 by 2 sine 2x. Right, so this gives us minus 1 by 3 x minus sine 2x by 3, and taking out minus 1 by 3 common, we get x plus sine 2x. Right, so this is a C1. Let's get to finding C2. C2 is given by the formula y1 R by W dx. This yields us cos 3x cosec x divided by 3 dx. This can be written as integral cos 3x divided by sin x, and we have 3 outside. Right, now I'm going to use the identity that cos 3x can be written as cos x plus 2x, and that can be written as cos a cos b in the form of cos a cos b minus sin a sin b. So I'm going to substitute this, and this implies that C2 has now the value 1 by 3 cos x cos 2x minus sin x sin 2x divided by 3, and we have the x in common. Now this 3 is already outside. This is sin x. Now this is 1 by 3 cos x. For cos 2x I'm gonna write it as 1 minus 2 sin square x minus sin x. Sin 2x is 2 sin x cos x. We have dx here divided by sin x. Right, the identities used are that 1 minus 2 sin square x is cos x, cos 2x, sorry, and 2 sin x cos x is sin 2x. Right, now taking the like terms, the regrouping with cos x as common, I get 1 minus 4 sin square x and divide by sin x dx. Now when I was at this junction, I could also have distributed this integral and separately integrated this term and this term. The answer would would be a little different from what I have calculated, but both the answers that we will find, that we would have found out, would still be suitable and acceptable. So I'm gonna go with continue with this. This is equal to, now I'm gonna take sin x as t, and this implies that cos x dx is equal to dt. So I'm going to substitute now. This gives us the integral as 1 by 3 integration 1 minus 4 t square divided by t, and this now becomes with respect to dt. So on dividing the integral, this gives us 1 by t dt minus 4 by 3 t dt. This gives us 1 by 3 in common log mod t minus t square. The integral of t is t square by 2, 4 and 2, the 2 gets cancelled, and this gives us 2t square, right? Yeah. So on substituting, I get 1 by 3 log mod sin x minus 2 sin square x. So basically this is our C2. So let's put these in the formula for yp, and we get that yp was c1 y1 plus c2 y2. So now it becomes y1 was cos 3x. So the value of c1 was minus 1 by 3. So this minus 1 by 3 x plus, it was minus 1 by 3 x plus sin 2x. So x plus sin 2x. And for y2, c2, the y2 was sin 3x, and from c1 we get the 1 by 3, and c2, sorry, we had got 1 by 3 log mod sin x minus 2 sin square x. So log mod sin x minus 2 sin square x. This is a yp that we have found, minus 2 sin square x, right? So this is a yp. Now let's substitute this value for y. Y we had was yh plus yp. So this implies y is a cos 3x plus b sine 3x minus cos 3x divided by 3x plus sine 2x and plus sine 3x by 3 log mod sine x minus 2 sine square x. This is our final solution that we have got. Now, just like I said, when we were on this junction, if we would have separated this, then answer would be a little would have come a little different, and instead of this 2 sine square the minus 2 sine square x term, we would have got a cos 2x term, which if we use the identity, then would also once again yield an extra would yield minus 2 sine square x, but with an extra constant term for c2, but the answer would still be acceptable.